Okay, so welcome to lecture number 12, and in this lecture, we are gonna continue this idea of a structure and relation in mathematics, right? And in the last lecture, I think at the end of the video, we got very quickly escalated into this definitions and kind of things at the end of the video, if you remember. And I think that was too quickly. I should step back and go a little slowly, and try to make you understand what's going on. Okay, so one thing I want to make clear about the last video is that when I said, and if you remember that, I said, uh, take a set, take a set. It could be anything, any abstract set X, and here we have the symbol belongs to that we use in set theory. And I said if we put together, we form a structure. But I also said it is not yet a structure, it can become a structure, right? Uh, but that is not the case. What I meant was a completely different kind of things. Because that X, I was not talking about one particular set, right? Because otherwise belongs to does not mean anything at all, right? It has a relation between element and a set, right? So I will make this thing clear later so we will start with this idea of a structure, and before that I would like to begin with a question. What is mathematics? It's a very important question. What is mathematics? Well, I think mathematics is study of structure, abstract structure. Now there can be too many types of structure. Various kinds of structure floating in the mathematical world, right? And the task of mathematics is to find the pattern in those structure and try to create different kind of structure. Now, what is structure now? The word that I keep repeating, right? This is an important question. The example of a structure is, for example, a group, right? A group is a structure, and we will learn what a group is in this video. A ring is a structure. If we go one level higher, we get field. A field is a structure. A vector space where vectors lives is a structure. And what is the use of a structure? Right? Why we have so many different type of structure? The reason is each structure has a different purpose. For example, take the example of field. Without field, we cannot do addition, multiplication, subtraction, and division. The arithmetic we learn is basically we are doing inside the field. If there is no field, we cannot do arithmetic, right? So the construction of field is we design the field because we want to do arithmetic, but it is not specific to arithmetic only. You see, it is more than that. If the field has the set of numbers and it satisfies those properties, then yes, we can do arithmetic, but it doesn't have to be number. It can be polynomials, right? So, okay, wait, yeah. So, the field we are talking about is very important because the very foundation, if we want to do the arithmetic, we should do inside the field, right? We cannot do arithmetic in group. You see, group is a different structure. Group can do very special kind of arithmetic. very special. It cannot do all of the arithmetic, And I will show you. I will demonstrate you what do I mean by that. We have vector space that is also a structure. So in mathematics, we have different kind of structure. As I said, for example, group. Then we have field, rings. Then we have let's say geometry, Euclidean geometry. That is also a structure. We have set theory. It is itself a structure. You see, vector space. It's a structure, right? Logic. It's a structure. Topology. It's a structure. So we have so many different kind of structure. Now, our task is to first see how can we classify to the structure. You see, we can put all those structure into two different groups at the beginning. Because later it will get so, yeah. So we have two different kind of structure we are going to work on, you see, and those two structure are algebraic structure. You see, we have two different kind of structure. The first one is algebraic structure and the other one is relational structure. You see, algebraic structure and relational structure. Now I will give you example of what do I mean by algebraic structure and relational structure. Not the definitions, only example. For example, geometry. Since we are talking about geometry a lot, I would give example of geometry. Euclidean geometry is an relational structure. Why relational structure? Because here we are not doing algebra. We are saying here is a point, here is a line, this point lies on the line or it does not lie on the line. This property of belongingness, a point belonging to a line, it is relation between point and a line. We are not doing algebra, we are simply saying this belongs to that, right? A point belongs to a line, it's a relation, it is not algebra. We say, given a two line on a plane, either they intersect or they don't. It's a relation, right? We are talking about the relation between line. What is the relation between this line and this line, right? We are not performing algebraic equation. We are just talking about a relation between two different objects or two same kind of object, right? So we can have two different kind of relational structure. Either that relation is defined among same type of object between line and line, like for example a line intersecting another line or two lines are parallel. This is the relation between two lines, right? Or we can define a relation between two different kind of object, point and a line, right? Or a plane and a line, right? So we have relational structure. So geometry, Euclidean geometry is an example of relational structure. Now what happens? A mathematician and a philosopher, René Descartes, he comes up and he says, all right. Okay, so he said, all right, can I translate, and this is important, this was a revolutionary idea, can I translate geometry of Euclid, which is a completely relational structure, into algebra? This is a very important question. I have relational structure here, which is Euclidean geometry, right? It's a very important thing, you see. So we have relational structure, which is Euclidean geometry here, And Rene Descartes comes up and he says, can I translate the language of this geometry, which is written completely in the language of relations, and put it into the another box of which is algebra? So can I translate Euclidean geometry from the relational structural language to algebraic structural language? Can I do that? And he did, and that is coordinate geometry. Yes. What is coordinate geometry? Coordinate geometry is, you take geometry, Euclidean geometry, since we are talking about Euclidean geometry only. So take Euclidean geometry that is given by Euclid, and here is algebra given by Al-Khwarizm. Now what is Rene Descartes doing? He is taking geometry and he is taking algebra and he is putting both of them together, you see. So we can move from one world to another world, a world of algebra to world of geometry, and world of geometry to world of algebra. It's a two-way connection, you see. And why this is possible? Why was this possible? Because algebra means what? Algebra means calculation, numbers, right? In algebra, what we do? We take a number, right? We take some input and we put it in a box and it produces some output, right? It takes an input, it processes it and produces an output. That is the algebra. But what is a relation? A relation does not produce an output. It only takes an input and shows the relation between them. Is there any relation or not? There is no calculation going on. It only says relation. For example, let's say there is a set of all the people living in this country, Nepal. Now the question is, it's a very important and it's a very easy question. The question is, so what we have? We have set of all the people living in this country, Nepal. That is a legitimate set, right? Now the question is, does Donald Trump belongs to this set? This particular set, the set of people living in the Nepal. He does not. So what it's trying to say? Are we calculating anything? No, we are not calculating. We are taking an element, right? A Donald Trump, the Donald Trump. That's an element, and here is our set of all the people living in this Nepal. Now we're trying to find a relation between them. Is there any kind of relation? We're not calculating number, you see. But in algebra, it is completely different. Take an example. 2 plus 2. We have two input, 2 and 2. We sum it and we get 4. That is output. 4 is an output, right? So Rene Descartes is doing these two things. He's taking geometry and translating it into algebra. Now, how did he do it? He did it because function. Yes. Function. This is very important. Algebra is about function. Without function, you cannot do algebra at all. That is the most important topic. Without function, you cannot do algebra. Now, why is that case? Because we want to calculate something, and to calculate something, we need a machine. Think very carefully. In algebra, we want to calculate something. We want to take inputs and do something with them, whatever you want to do. Just do, and it produces some output. Now this process, take input and process it and produce an output. This is what machine is. Take an example of computer. What does a computer do? A computer takes input, right? Array of input it can take. It can take one by one a linear input or a parallel input, and that is not important. A linear input would be a function with one variable. Parallel input would be the function of many variables. of so therefore, and this is not about fast and slow, you see. A computer working on one variable is not slow, and a computer working on many variables is not fast. It is not about it is not about fast and slow. It's about problem solving. What does this problem need? If this problem need one variable, then that is enough. Why necessarily use hundreds of variable and drain the energy, right? So, but in some cases, the parallel variable is very important. It's become way faster, right? Now, so this input and process and then output, it is a machine, and every machine in this world has to go through this structure. Every machine, whatever you can imagine, any machine. A machine, this is the called principle of machine given by Charles Babbage, the father of computer, that a machine needs this three things: an input variable, and then a device, and that device will accept those input variable, and then in the device we have circuits, and that circuit will manipulate those variable based on what we want to do with that variable, and then it gives an appropriate output, right? So algebra is the same thing. Algebra is this: we want some input and process it, and then we want some output. So it is a machine. So it means to build algebra we need to build a machine, and that machine is function, right? That machine is function. So but we know already the function. A function can be built using relations. You see, what is a function? It's a special kind of relation, that's all. Or is it not? If you remember in your school class, we read ordered pair, then we read Cartesian product, and then we read relation, and then comes the function. And the order is not random. The order is what matters. We first read ordered pair, then Cartesian product, then relation, then function, because a function, we are building functions, we are building mathematical machines, right? So the theory is any relations that is given, okay, so any relation that is given to us, we can translate them into function. We can. A relation can be translated into a function, but not all relations. You will lose the information, you see, because translation is not perfect, 100 perfect always. We are going to lose lots of information there, you see. And coordinate geometry was the revolutionary point because it tried to take one structure, which is a relational structure, and translate it into an algebraic structure, right? And we will see how can we do that, right? So in the next lecture, I think we'll try to do this, right, and see what I'm trying to say mathematically. So for now, thank you for listening.